Welcome back to Minerva Tutors TV and the GCSE/IGCSE Chemistry series. This lesson follows on from the Ionic, Covalent and Metallic bondings lesson. So if you haven't seen that one yet, go and watch that one first before you come to this one, where we'll be talking about the change of state of matter, nanoparticles and polymers. So matter exists in one of three states: solid, liquid or gas. When it exists in a solid, the particles in this matter are arranged side by side and they don't move. They're in these fixed positions in rows, in columns, like so. As you can see with ice, the example we've chosen to use over there. They don't move, these particles, but they do have some energy. So they do vibrate from side to side very, very slightly. In a liquid, the particles have more energy and they've broken free of this uniform linear structure, and these particles are free to flow over the top of each other, and that's why liquids will often flow if poured. If we look at a gas as well, these particles are even further apart. They're free to move about, even more free to move about. They move randomly in all directions at random speeds as well. If we're going from a solid to a liquid and we're changing state, we call that melting. And we get melting whenever we're adding heat energy to the solid, because what happens when we add heat energy to the solid is the particles themselves get more energy. They get more what we call kinetic energy, and that's the ability to be able to move apart or move around. So when we're adding this heat energy or this kinetic energy to a solid, the particles get more energy, they start vibrating more. Eventually they'll be vibrating so much that they'll move out of their fixed positions and form the liquid formation, as we can see in the middle of solid and gas there. Once we've got this liquid formation, we can continue adding heat energy, which continues to give the particles more kinetic energy, and they'll move about even more and even more until eventually the liquid will boil, and it will boil and turn into a gas, where the particles, like we say, are really spread out, moving in random directions. The gas particles have the most energy, the most kinetic energy, and moving with the highest speeds in those random directions. If we then take that gas and we cool it down and go back the other way, this is called condensation. If we're cooling it down, we're giving those particles less kinetic energy. So they move around less, they start to get closer and closer together until we form the liquid formation that we've got back there. So going back there again, the particles can flow over each other. If we take away more heat energy, so if we make this liquid colder and colder and colder, the particles again will have less kinetic energy until they get so close together that they form the solid structure again. Now, it is possible to go straight from a solid to a gas and skip the liquid stage. This is called sublimation or subliming, and it requires really, really high temperatures and really high amounts of energy to give the particles enough kinetic energy to be able to break free and then spread apart, going straight from a solid to a gas. Last lesson, we looked at ionic bonding, and we said that ionic bonding normally forms these things called giant ionic lattices. We said a couple of things about them. We said that they normally have quite high melting and boiling points, and that they can't conduct electricity because the particles can't move unless these giant ionic lattices are molten. Now, we also said that they're formed because of the strong electrostatic forces between the positive ions and the negative ions. And because there's a lot of them, the strong electrostatic forces holds it in this rigid structure here. And we can obviously now see that this is a solid structure because the particles are arranged really closely together in the uniform shape, side by side, in this linear structure. If we compare that to the simple covalent structure we looked at last week, we looked at water here, we can see it's a lot different. With water, the particles are more spread apart at room temperature. They're more in this gas/liquid formation where they can flow and move apart, and they've only got weak intermolecular forces holding them together, which we said last week we gave them quite low melting and boiling points. We also said they can't conduct electricity because they're not charged particles, despite the fact they can move about. So this, often simple molecular structures will be liquids and gases as well. Now, with covalent bonds, we can also form things called polymers. Now, a polymer is a long chain of many repeating subunits. repeating again and again and again. And by a subunit, we just mean a smaller molecule or smaller compound. In this case, I've chosen ethene. Now, if we were to take ethene and take lots of ethene molecules and join them end to end to end to end, have a really long chain, we could draw that out and it would look like just a really long chain of carbon, 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 carbon with loads of hydrogens on. But drawing that out would take a lot of time. So we tend to draw it out like what we've got here inside the brackets, where I've put my repeating unit, the ethene repeating unit. You can see the double bond that was previously in the middle has opened up to be able to join to other ethenes. So that's why we've got the C to C with 2 H's above, 2 H's below, and then 2 lines going out on the side to show that there are other ethenes joining onto this. We've put square brackets around it, again to show this is the repeating unit. And there's a little n outside the bracket. Now that n stands for how many times this unit is being repeated. So if we had 100 ethenes all joined together in a chain, then n would be 100. And we'd have 200 carbons all in all, and 400 hydrogens all in all, like so. And this process of joining the ethene molecules together, or just the smaller subunits together to form a polymer, like polyethene, like what we've got there, is called polymerization. So when we're forming a polymer, it's called polymerization. The last bit on this section is all to do with nanoparticles. Now, nanoparticles are particles. They can still be solid, liquid, or gas in that formation. They're just really, really small. The definition is that it is very small substances containing at least or around about 100 atoms. So for size and for scale, we've got this table here. An atom itself will be about 0.1 nanometers wide. A nanoparticle is 1 to 100 nanometers wide. Comparing that to real life things that we know about and see, fine particles we've got in there / particulate matter, that's sort of pollutants that can be found in the exhaust of cars. Again, we can't see these pollutants. They're about 100 to 2,500 nanometers in wide. The coarse particles are things that often we just call coarse particles, dust. We're starting to be able to see the particles at this point, 2,000 to 10,000 nanometers wide. And for reference, a better frame of reference is the thickness of paper that is 100,000 nanometers wide. So that just goes to show that the thickness of paper is about 1,000 times wider than a nanoparticle. So we're talking about really, really small particles here. Nanoparticles are useful, and the reason why we're talking about them is that they have a lot of uses, and a lot of the uses hark back to the fact that because they're so small, they have a really large surface area to volume ratio, because what we're taking is, if we were taking a particle that was about the size of a cube, about that size, and breaking it down into nanoparticles, we've still got the same volume because we're breaking apart that cube. But as we break it apart, every time we're increasing the surface area. Now, it's quite good to have a high surface area for things like speeding up a reaction, as we'll look at later in the chemistry series. If we've got something with a larger surface area, the reaction happens more quickly. Nanoparticles are often used as things called catalysts, because catalysts do exactly that. They speed up a reaction. Other uses of nanoparticles, not only do they make good catalysts, but another good use is in cosmetics. So things like sun creams will contain nanoparticles. Again, because they've got this such large surface area to volume ratio, they cover a lot of the surface of your skin, but they do not, they're not visible to the eye. Meaning that when we use these sun creams that contain nanoparticles, we actually can't see the sun cream itself once it's been rubbed in, because we can't see the nanoparticles. The same with a lot of cosmetics and makeup products as well. You won't be able to see the marks that they're making, but they will be present there, and they will still provide UV protection because they're still physically there blocking the UV rays from the sun. Other uses of nanoparticles are nanotubes, for example. So we talked about graphite last time, and how graphene is a sheet of graphite, and it can be bent into a tube-like shape or a fullerene shape. We'll come on to fullerenes in a minute, but if it's in a tube-like shape, this nanotube, these nanotubes can conduct electricity. They're obviously also very lightweight because they're only made of a few hundred atoms. So because they can conduct electricity and because they're lightweight, they're often used in microchips, because if you want a computer chip for your phone, you don't want it to weigh a ton. you want it to be as light as possible and as efficient as possible so that you can carry it around and it's not going to be a pain to carry this huge weight around. So nanoparticles are often used in microchips, in cameras, in phones, things like that. Other uses, if we go into the fullerene is, again, a sheet of graphene curved into a ball-like shape. Now, fullerenes are often used as drug delivery tools in that they provide a hard outer coating for a drug, so it's more able to specifically target an organ of the body or an area of the body that you want to target without being broken down. It's got this harder outer layer. Other uses for nanoparticles in general, nanoparticles are often used as a lubricant for gears or artificial joints as well, and that's simply because of their small structure or their small size, being able to move over the top of each other and flow over the top of each other makes them quite slippy. They can also be used for stronger, lighter building materials, again because they're quite strong, because graphite, if we look at the nanotubes, for example, very, very strong because they're made up from a layer of graphene, which we know from graphite contains carbon bonded to 3 other carbons using strong covalent bonds. So we've got these strong covalent bonds that need a lot of energy to break them down, making nanotubes, nanoparticles, fullerenes all very strong and useful. So that wraps up the bonding section of the chemistry series. If you enjoyed it or found it useful, please check out some of the other Minerva Tutors TV chemistry series videos.